you may tell your team members that, okay, what would be the benefit if we check this plan, and what about the other plan? So the benefit and the cost. But some people without the training may not give you a perfect answer to the problem, to the question. But since you are a leader and a trained leader by economics, you may give some beautiful solution or beautiful insights of the problem. You may see the benefit, the cost. Okay? So, of course, everybody can say, oh, the benefit, the cost. But what is the precise, or what is the exact benefit, and what is the exact cost? So, in terms of money, or in terms of utility, and you may perfectly interpret the results. Okay? So we have the condition here. We may also interpret the first order condition, and of course we may have the implicit function Q1 star, Q2 star, and lambda star. But now it is P1, P2, and U bar. No more Y. You don't see any Y in the problem here. So we have what kind of variables we have? In the problem we have P1, we have Q1, we have P2, we have Q2, we have U bar. Totally 5 variables, right? And an additional variable, lambda, is added because we apply the method of Lagrangian function. So the Lagrange multiplier approach, due to this approach, we have an additional variable, lambda. So we have totally 6 variables now. P1, Q1, P2, Q2, U bar, lambda, 6. And we choose over Q1, Q2, and lambda. So these 3 would be endogenous variables. And the other 3 variables would be exogenous, which is P1, P2, and U bar. Because we changed the problem, okay? Remember now, the environment will be the utility level you require me to reach. I want to attain or to reach or to target to reach, to attain. The level you require me to complete, to achieve, to finish. Okay? And given the market prices of good 1 and good 2, P1, P2, so I try very hard to find the optimal solution. So U bar, P1, and P2 are variables external to my decision. I just cannot change these variables. I got to accept them. Okay? Given these variables, exogenous variables, and we choose over Q1, Q2, and lambda. So our choices, Q1, Q2, and lambda, will be functions of P1, P2, U bar. P1, P2, U bar. P1, P2, U bar. All right? Yep.
The utility and P1, P2 are exogenous variables.
Okay, now we want to minimize 5Q1 plus 2Q2 subject to Q1, Q2 equals, what is that? 2490 You don't see $300, right? You don't see that. Okay? Now, this would be U bar. And the Lagrange would be 5Q1 plus 2Q2. This is our target, the expenditure. Plus lambda and 24 squared 90 cubic minus, Q2 squared Q1 squared Q2 cubic. And Lagrange 1 would be 5 minus 2Q1 Q2 cubic. Is that right? And Lagrange 2 equals 2 minus, I lost something, 2 lambda. And 3 lambda Q1 squared Q2 squared. Okay? And 5 by 2 equals 2 by 3, and lambda is cancelled, and Q1, Q2, right? Okay? So Q1 equals Q2. And we replace this into the budget constraint. 24 squared 90 minus Q1 is 15, 4, Q2 squared Q2 cubic. This would be 0. Okay, now 3, 8, 6, 15, 4. Okay. 24 is 6 times 4 squared, and 90 would be 6, 15. Is that right? Okay? So it would be something like 6 to the power of 5, 4 to the power of 2, 15 to the power of 3. The requirement. And here we have Q2 to the power of 5 and 4 to the power of 2 and 15 to the power of 2. So they have to be the same. So this equals this, and 4 squared and 15 now is be 5, right? So Q2 to the power of 5 would be 6 to the power of 5 and 15 to the power of 5. It would be 90 to the power of 5. Okay? So Q2 star would be 90. And Q1 star would be 24. And the expenditure would be 120 plus 180, $300. So $300 would be the optimal expenditure here. reverse problem, and we got the same solution. Do you think it's beautiful here? I think it's pretty beautiful, the dual problem, duality. So you see, I just gave you a utility maximization, a numerical example. So I gave you the utility function of Q1 squared Q2 cubic, and I gave you 5Q1 plus 2Q2 equals $300. This is something I just come up to my mind and just put it down, and we have solutions of 2490. So in that case, I gave you a budget constraint, and you need to push out the utility level, the indifference curve, to push it outward, to push the indifference curve outward. Try very hard to maximize the utility, okay? So they have a cut point, or the tangent point, which is the solution of 2490. And we got this solution, we replace it back to the utility function, So we have the solution here. It is the U star in this problem. But now, we reverse the problem here. I want you to minimize the expenditure. I want you to minimize your expenditure so that the requirement of the utility function is this. So the result in the previous problem is now the requirements I want you to reach. I want you to achieve, to attain. Okay? And I didn't give you any kind of income because the issue is reversed, is changed. Now you need to find the optimal solution of the expenditure. You want to minimize the expenditure. And you see the expenditure would be $300. So what happened here is, if I give you a $300 budget constraint, and you try to maximize your utility, so you may reach the utility would be 24 to the power of and 90 to the power of 3. Now, I change the problem here, and I give you the requirement 24 to the power of 2, 90 to the power of 3, and I ask you to minimize the expenditure. And you will find the minimized expenditure would be $300. Okay? So, given $300, you got to maximize your utility. You've got to push outward the indifference curve. But given the indifference curve, you need to minimize your expenditure. And it happens to be the same solution here. 2490. 2490. Okay? But basically, these are two different problems. Utility maximization, expenditure minimization. Okay? Okay, let's take a break. It's 10:53 now. 11:05.